In 1907, Oskar Fischer read dementia plaques not as inert lesions, but as the physical residue of a dynamic biological process. Today, we know the plaque is not the primary driver of cognitive decline. The strongest physical correlate of memory loss in Alzheimer's disease is actually the loss of the synapse itself. To understand why a synapse fails, we have to look at how it holds its shape. A dendritic spine is held open by an actin filament network, and that balance is centrally regulated by one protein, cofilin 1, at a single amino acid, serine 3. When serine 3 receives a phosphate group, cofilin cannot bind and the actin network remains stable. When the phosphate is removed, cofilin binds to the filaments and severs them, collapsing the spine. If synapse loss drives Alzheimer's, knowing the state of this specific switch is critical. Yet looking at human Alzheimer's tissue, the field cannot agree on which direction the switch is thrown. Despite decades of research, the physical structure central to cognitive decline rests on a biological switch whose basic pathological state remains unresolved. The published literature contains a direct contradiction. One camp shows that amyloid beta acts through an immune receptor to remove the phosphate, causing pathology. Another camp shows that amyloid beta adds the phosphate through Rho-kinase, which is reported to be equally toxic to the synapse. Right now, Rho-kinase inhibitors are in development for this indication. This means we are targeting a residue without a consensus on the intended sign of the therapy. This diagram shows the biological architecture causing the contradiction. Two opposing chemical pathways control the synapse. The Rho-A contractile arm shrinks the spine, while the CDC42 protrusive arm grows it. Both cascades converge on the exact same kinase. Because they share this step, both pathways write the identical phosphate mark onto serine 3. This creates a many-to-one collapse in the information the signal carries. An antibody cannot differentiate a spine collapsing under pathological stress from a spine growing under a protective stimulus. Bulk measurements of this residue are uninterpretable in principle. To find the true pathological signal, we have to look one layer up the biological stack. One layer up sits affexin 5, an exchange factor that dictates the behavior of the actin machinery. Its control node is a specific site, tyrosine 361. This site uses a dual-function design. When a phosphate attaches to tyrosine 361, it activates the molecule to shrink the spine. But that same mark simultaneously attracts a ubiquitin ligase and marks it for the proteasome. The active molecule is pulled into the cell's disposal machinery and completely destroyed. In this design, the more strongly the signal is sent, the more completely the transducer is consumed. Why use destruction instead of the simple phosphatase to switch the signal off? A phosphatase only resets a chemical mark. It leaves the signaling protein physically present in the synapse, where noise can trigger it again. To deliver a brief instruction, a synapse's control surface must be terminated by physical destruction. Therefore, this means an abundance of this protein is the true signature of a failed signal, not an amplified one. This same timing architecture also governs the cell's protective renin pathway, which operates through an adapter protein called disabled 1. Phosphorylation activates the protective signal, but simultaneously targets the adapter for proteasomal degradation. The signal is designed to be transient. Remarkably, both of these opposing arms, the destructive and the protective, are written by the exact same enzyme, the kinase FINE. Blocking FINE removes the pathological toxicity, but it also uncouples the synapse's required protective brake. FINE is a shared enzyme serving opposed clients. You cannot safely treat the disease by attacking the shared writer of the signal. So how does Alzheimer's disease specifically exploit this timing design? Amyloid beta binds to the licensing receptor, EAP-B2, and violently feeds the receptor itself into the proteasome. Without that receptor to authorize the destruction of affexin 5, the effector protein accumulates indefinitely. The resulting Alzheimer's dendrite holds a pool of affexin 5 that is abundant, locked into a contractile state, and unscheduled for destruction. This is not a loss of clearance in the general sense. The proteasome is intact. Amyloid's action is a gain of degradation. It presents the wrong substrate to a working machine. The proteolytic system is executing the wrong instruction, creating a chronic signaling loop that the cell can no longer switch off. If signal termination relies on physical destruction, the cell's sorting system becomes a critical bottleneck. Clinical evidence confirms this. Enlargement of the early endosome is the absolute earliest known structural abnormality in Alzheimer's. present before any amyloid deposition appears. The primary risk factor, ApoE4, sabotages this system. It causes protective receptors to be sequestered inside compartments rather than recycling to the surface. The receptors are not missing or mutated, they are trapped in the wrong compartment, effectively deafening the neuron to protective signals. This structural logic helps explain why targets like Rho-kinase and FIN are so difficult to hit. An intervention that matches this logic is the repair of the cellular clock. Inhibiting a proton channel called NHE6 reverses the ApoE4-induced recycling block and restores receptor traffic. This suggests a strict ordering for treatment. You must repair the cell's sorting capacity first, before supplying a protective signal or ligand. No quantity of a drug will fix a receptor that is in the wrong cellular place. Oskar Fischer read a deposit as the residue of a process. Alzheimer's is a failure of proteolytic timing, and until we prioritize repairing the cellular clock, we will continue to misread the residue.